In this session on vector analysis, we will discuss about divergence of a vector and its physical significance. Divergence of a vector. It is represented by del dot A. If vector A of xyz is equal to ax I cap plus ay j cap plus az k cap be defined and differentiable at each point x, y, z in a region of a space. Then the divergence of a vector A is dot product of del and vector A. Therefore, divergence of vector A is equal to del dot A is equal to I cap dou by dou x plus j cap dou by dou y plus k cap dou by dou z dot ax I cap plus ay j cap plus az k cap, where I cap, j cap and k cap are the unit vectors along x, y and z direction respectively. Therefore, divergence of a vector A is equal to del dot A is equal to I cap dou Ax divided by dou x plus j cap dou Ay divided by dou y plus k cap dou Az divided by dou z. This is the divergence of the vector. Divergence of a vector is a scalar quantity. Physical interpretation of divergence of a vector. To study the physical interpretation of divergence of a vector, let us draw rectangular parallel piped figure. This is the rectangular parallel piped figure whose edges are delta x parallel to x-axis, delta y parallel to y-axis and delta z parallel to z-axis respectively. Let us consider a vector A at a point P whose coordinates are x, y, z. Then the vector A is resolved. Vector A at a point P is resolved into three components AX, AY and AZ, three rectangular coordinates. The value of the divergence of the vector A is equal to the total outflow of the vector A, total outflow of the vector A over the six faces of this rectangular parallelepiped per unit volume. The coordinates at the center of the face 1 are x plus delta x by 2, y, z. The outflow of the vector over the face 1 and over the face 2, which is perpendicular to x-axis, is entirely due to the component of the vector A, that is Ax. Let dou Ax by dou x be the rate of flow of vector along x-axis. Hence, the flow of vector at the center of the face 1 is given by Ax plus dou Ax by dou x into delta x by 2. That is vector at P plus unit change in vector along x-axis into distance delta x divided by 2. The net flow of vector from the face 1 is given by Ax plus dou Ax by dou x into delta x by 2 into delta y delta z, where delta y delta z is the area of the face 1. Therefore, the net flow of the vector from the face 1 is Ax plus dou Ax by dou x into delta x by 2 into delta y delta z, and this is in the outward direction from P, and the direction of this vector is outward from the point P. Similarly, the net flow of vector from the face 2 is given by Ax minus dou Ax by dou x into delta x by 2 into delta y into delta z. This is directed inward from P. Then the net flow of vectors along x direction, that is from the phase 1 and from phase 2, is given by Ax plus dou Ax by dou x into delta x by 2 into delta y into delta z minus into bracket Ax minus dou Ax by dou x into delta x by 2 into delta y delta z. After simplification, we'll get it's equal to 2 dou Ax by dou x into delta x by 2 delta y delta z. 2 gets cancelled. After complete simplification, the net flow of the vector along x direction is dou Ax by dou x into delta x, delta y, delta z. Similarly, the net flow of vector along y direction is dou Ay by dou y into delta x, delta y, delta z, and net flow of vector along z direction is dou Az by dou z, delta x, delta y, delta z. Therefore, the net flow of vectors is equal to dou Ax by dou x, delta x, delta y, delta z plus dou Ay by dou y, delta x, delta y, delta z plus dou Az by dou z, delta x, delta y, delta z. After simplification, taking common delta x, delta y, delta z, we get the net flow of vectors is equal to dou Ax by dou x plus dou Ay by dou y plus dou Az by dou z into delta x, delta y, delta z. Then if we'll calculate net flow of vector per unit volume, we get net flow of vector per unit volume is equal to dou Ax by dou x plus dou Ay by dou y plus dou Az by dou z delta x, delta y, delta z divided by delta x, delta y, delta z. These two cancel each other. Therefore, the net flow of vector per unit volume is equal to dou Ax by dou x plus dou Ay by dou y plus dou Az by dou z, where delta x, delta y, delta z is the volume of the rectangular parallelepiped. So therefore, net flow of vectors per unit volume is equal to divergence of vector A, or is equal to del dot A. Therefore, divergence of a vector is net flow of vectors per unit volume. This is the physical interpretation of divergence of a vector. So, from the physical interpretation of the divergence of the vector, it follows that divergence of a vector is net flow of vectors per unit volume. Physical significance of divergence of a vector. The divergence of a vector is net outflow of vectors per unit volume. If divergence at a point is positive, then flux expands or flux leaves from that point, and that point is called as a source of that vector. If divergence at a point is negative, then flux contracts. Flux enters to that point, and that point is called sink of that vector. If the divergence is 0 at a point, then the amount of flux entering is equal to the amount of flux leaving. For small volume, concentration of vector field line is maximum and vice versa. Hence, divergence is maximum for near to source and vice versa. Up to now, in this session, we discussed about divergence of a vector. The divergence of a vector A is the dot product of del and vector A and is given by divergence A is equal to del dot A is equal to I cap dou AX by dou X plus J cap dou AY divided by dou Y plus K cap dou AZ divided by dou Z. And divergence of a vector is net outflow of vectors, net flux flow per unit volume is the physical significance of divergence of a vector. The net flow of vectors per unit volume is equal to dou AX by dou X plus dou AY by dou Y plus dou AZ by dou Z and is equal to divergence A is equal to del dot A. Thank you.